Assalamualaikum and good morning. So today our group will present about our assignment for subject BEET 3373 Digital Signal Processing. So first of all, I will introduce myself. My name is Abdul Hakim bin Hamzah and my teammates are Muhammad Iqbal bin Muhammad Rozai, Shavin Raj anak lelaki Nada Rajan and Muhammad Iqbal Aiman bin Muhammad Zulfikri. So our lecturer is Puan Izzadora binti Mustafa and our assignment title is CHEBYSHEV Filter Design. So this is our introduction for filter design. Filter design refers to the process of designing a filter, which is a device or algorithm that selectively allows or blocks the passage of certain signals or components of a signal while attenuating others. Filters are widely used in various fields, including signal processing, electronics, telecommunications, audio engineering, and image processing. The design process involves specifying the filter type, order, and parameters such as cutoff frequency, bandwidth, and ripple. Various mathematical techniques, optimization algorithm, and software tools are employed in the design process. Filter design is crucial in application where signal processing or selective signal attenuation is required to meet specific performance criteria. Common applications include audio equalization, image processing, communication, control system, and biomedical signal processing. So there are a lot of filter types such as low pass filter, high pass, band stop, Butterworth, Chebyshev, elliptic, FIR, and IIR filter. So today we will focusing on Chebyshev filter, which is the number 6. So this is the introduction for CHEBYSHEV filter. A CHEBYSHEV filter is a type of analog or digital filter with a frequency response that achieve a steeper roll-off between the pass band and the stop band compared to a Butterworth filter. The key characteristic of a CHEBYSHEV filter is that it allows for ripples in the pass band in the exchange for a faster roll-off. So this is a CHEBYSHEV filter for type 1. Actually, CHEBYSHEV filter get a two type, which is a type 1 and type 2. So this part is for type 1. So this filter allows for ripples in the pass band but has a monotonic roll-off in the stop band. The pass band ripple is typically specified as a parameter called a ripple factor or pass band ripple. CHEBYSHEV type 1 filters are commonly used when a faster roll-off is required and some passband ripple is acceptable. So as shown in the figure in the slide, the waveform are for Chebyshev type 1. So this is a mathematical equation for Chebyshev part 1. So the first equation is for gain and the second one is for ripple vector. And the last one is 3 dB frequency omega h is related to omega naught by using that equation. So this is a Chebyshev type 2. This filter allows for ripple in the stop band but has a monotonic roll-off in the pass band. The stop band ripple is specified as a parameter called stop band ripple or attenuation. Chebyshev type 2 filters are employed when a faster roll-off is needed and some stop band ripple is acceptable. So as shown in the figure in the slide, the waveform is for Chebyshev type 2. So this is a mathematical equation for Chebyshev part 2, which is the first equation is for gain, the second one is for ripple factor, and the last one is the 3 dB frequency. Frequency h is related to frequency naught by using the equation. So the characteristic of Chebyshev filter. So Chebyshev polynomial defined by recursive formula. So the formula is for recursive formula, and for odd values of n, the oscillator curve start from unity, while for even values of n, the oscillator curve start from 1 over 1 plus omega squared. So the left one is for odd, which is start by unity, and the right side is for even, which is start by that equation. So I will pass to Iqbal Aiman for the next presentation. Thank you.
So for the comparison between the Butterworth filter and Chebyshev filter is for the magnetic response for Butterworth filter is decrease monotonically as the frequency ohm increases from 0 to infinity. And then for the magnetic response of Chebyshev is Chebyshev filter exhibits ripples in the passband or stopband according to the type. The second one is the transition band. For the Butterworth is more in Butterworth filter, but for the Chebyshev filter is the transition band is less. After that, the poles of Butterworth filter lie on a circle, and the pole of Chebyshev filter lie on an ellipse. For the same specification, the number of poles in Butterworth are more when compared to the Chebyshev filter, and the order of Chebyshev filter is less than that of Butterworth. This is the greatest advantage because less number of discrete components will be necessary to construct the filter. This is about Chebyshev 2 or inverse of Chebyshev. Chebyshev 2 filters are similar to Chebyshev filters. However, Chebyshev 2 filters differ from Chebyshev filter in the following ways. The first one is Chebyshev 2 filters minimize peak error in the stopband instead of the passband. Minimizing peak error in the stopband instead of the passband is an advantage of Chebyshev 2 filters over Chebyshev filter. The second one is the Chebyshev 2 filter have an equiripple magnitude response in the stopband instead of the passband. Chebyshev 2 filters have a monotonically decreasing magnitude response in the passband instead of stopband. Chebyshev 2 filters have the same advantage over Butterworth filter that Chebyshev filter have a sharper transition between the passband and the stopband with a lower order filter, resulting in a smaller absolute error and faster execution speed. The Chebyshev 2 filters have the following statistics. The first one is minimization of peak error in the stopband. Equiripple magnitude response in the stopband, monotonically decreasing magnitude response in the passband, sharper roll-off than Butterworth filter. For the application of Chebyshev Chebyshev 1 filter applied for noise suppression in ECG signal. In many medical applications, there is need to remove frequency components from a signal while leaving rest of spectrum unaltered. While recording ECG signal, it gets corrupt due to different noise interference and artifacts. Noise and interference are usually large enough to obscure small amplitude features of the ECG that are psychological or clinical interest. The, the bandwidth of the noise overlaps that of wanted signals, so that simple filtering cannot sufficiently enhance the signal to noise ratio. The Chebyshev 2 and Chebyshev type 2 filters are applied on the ECG signals. How does ECG works? An electrodiagram ECG is the recording on the body surface of the electrical activity generated by the heart. ECG signal is a barometer. ECG is signal is ECG signal is a biological multi-channel signal recorded from a system of electrodes of the ECG device. This is the fifth order Chebyshev filter. The frequency response or time domain characteristic of the filter and the order primarily depends on the transfer function. For example, one can build For example, one can build a fifth order CHEBYSHEV or Butterworth filter with a certain key topology, while someone else may choose to implement the same on different topologies such as multiply feedback. So this is the first stage of diagram, and this is the second stage of diagram, and this is the third stage of diagram. So this is the fifth order Chebyshev filter. So this is the seventh order Chebyshev filter. A seventh order Chebyshev filter specifically refers to a filter of order 7. The filter order represents the degree of the filter transfer function. The transfer function of a Chebyshev filter is characterized by its passband ripple and its ability to achieve a sharp transition from the passband to stopband. That's all from our group. Thank you.
Yes, I'm Kumpuan. I will continue presenting. By the way, my name is Muhammad Iqbal. Okay, for the first part is low pass Chevy type 1 filter. For the FC is 300 cut off frequency. The FS is 1000 sampling frequency. Okay, for this part is this function return the numerator and denominator coefficient of the filter transfer function. So the B is denominator and the A is numerator. The number 6 is for filter order. The number 10 is for ripple factor. And this equation is for normalized cut-off frequency. Okay. For this line, function visualize the magnitude and phase response of the filter. Okay, when we run, we got this output for the first part. Okay, for the second part, high pass, this ZPK is for the filter coefficient. It represent 0, pulse, and gain. Okay, for the 9, the first 9 is for filter order. The 0.5 is for ripple factor. 300 over 500 is for normalized cut-off filter frequency, and the high is specific that it is a high pass filter. Okay, when we run this program, so this is the output for high pass filter. Okay, next is band stop filter. Okay, similar to the from the past example. Okay, for the first, the number 3 is for filter order. Number 5 is for ripple factor. 0.2 and 0.6 is the stop band frequency, normalized to the Nyquist frequency, 0.5. In this case, the stop band is from 0.2 to 0.6, creating a band stop filter. Okay, when we run this section, okay, we will get this output for band stop. Okay, next is band pass. Okay, for the band pass, 10 is for filter order, 3 is for ripple factor, 500, 560 over 700 is for passband frequency. Normalized to Nyquist frequency 0.5. Okay, for the design fillet, is used to design band pass IIR filter. Okay. For this below part is convert the state space represent to second order section. Okay, when we run this part, the output we get is like this. Okay, this is for band pass filter. Okay, for the last one, this part I will compare each filter from IR filter. So we got butter, CHEBY1, CHEBY part 2, ellipse and BSEF filter. Okay, this is the output that we get. As you can see, the blue one is butter, the red one is CHEBY1, the yellow one is CHEBY2, the purple one is ellipse, and the last one green is BSEF. So this is all the example filter that IIR filter got. Okay, that's all for me. Thank you.
Hello everyone. Today I'm going to present about CHEBYSHEV Type 2 transfer function, MATLAB coding and the output. First of all, we're going to see about the low pass CHEBYSHEV Type 2 filter. This line FC defines the passband edge frequency in Hertz, and Fs is 1000, which is top band edge frequency in Hertz. And the second line, B, A, this defines the 6th order CHEBYSHEV Type 2 filter. And then for the FC, for the plot frequencies, the range is -100 and 20 dB. So the Y is the axis limit. When we run this section, we can see this as an output. The magnitude and the phase decrease, which is the frequency plot diagram. For the second part, we're gonna see about the high-pass CHEBYSHEV Type 2 filter. This line shows the design of 9th order CHEBYSHEV Type 2 filter. Okay, at the MATLAB function FV tools we used in this code to plot the filter frequency. Okay, the CHEBYSHEV 9 is about specification of the filter order, and the 20 is the top band attenuation in decibel, and 300 over 500 is about, the 300 is first part is about high pass cutoff frequency, and the 500 is about the increased frequencies. And the SOS2P2 source line, this line shows the convert of filter poles and zeros to the second order section. When we run this section, we can see this as the output. Okay, this is the output for the high pass CHEBYSHEV Type 2 filter. For the third part, we're going to see about the bandpass CHEBYSHEV Type 2 filter. The first line shows the bandpass filter line, and then the 10 is the specification of the filter order, and then the 40 is about the stop band attenuation decibels. 500 over 560 over 750 defines the passband frequencies as the fraction of the increased frequencies. This line shows the design of a bandpass IR filter using design field. And then we're going to use the SOS MATLAB function, which can convert the transfer functions coefficients to SOS format. We also used FVT equals to FV tools, which can compare the responses between both filters. When we run this section, we're gonna see this as the output. Okay. This shows the output for the bandpass CHEBYSHEV type 2 filter. Next, we're going to see the bandstop CHEBYSHEV type 2 filter. This line shows the third order bandstop CHEBYSHEV filter. The 3 is equals to specification of the filter order, and then the 50 is equivalent to stop band attenuation decibel, and 0.2 and 0.6 is defines the pass band frequencies. When we run this section, we can see the magnitude and the phase degrees. This shows the frequency plot diagram. Next, as the last of CHEBYSHEV type 2 filter diagram MATLAB output, we're gonna see the comparison of analog IR low pass filters. Here we're gonna see about 4 types of filters here. First one is about the Butterworth low pass filter, and the second is about CHEBYSHEV type 1 filter, and the third one is CHEBYSHEV type 2 filter. The last is elliptic filter. When we run this section, we can see the output something like this. This shows that the blue color is the Butterworth filter, and the red is CHEBYSHEV 1, and the yellow is CHEBYSHEV 2, and the purple is ellipse filter line. The H1 here we can we can see that H1, H2, HE and HB is equivalent to these filters, type of filters. That's all from me. Thank you very much.